Okay, so I wanted to post this video to kind of give one last example of how we use Maxwell's equations. So we've already learned about what they are, but let's actually see what we can do with them and how we can actually find solutions and what those things mean. So just as a bit of an overview here, we're going to go through a couple of specific solutions. I'm going to show some ways that we manipulate the equations, but I think the bulk of your actually understanding is going to come from when you go through the Maxwell's equations worksheet after you watch this here. So that's actually going to be, I think, what will be really helpful for you. Um, so let's look at this here. We have Maxwell's equations. We've derived these in class. You should all be experts on them. But today we had, in lecture, we looked at what happens if we write the equations in a vacuum, specifically if there are no electric charges and if there are no currents. And what we get is a set of four equations that look a little bit more simple, a little bit more symmetric here. So the first two, the divergences of the E and the B field. Now, what these equations here mean is that if there are no charges present to create the electric field or magnetic field lines, or to terminate those magnetic field lines at, that no divergence implies that there will be no, the fields will be continuous. They won't start or end. You're not in, when you're in free space, you're not going to get a field that just appears out of nowhere, or you're not going to get some electric field line that comes in and terminates at some point, because you need charges for that to happen. So the cool thing is that Maxwell's equations, even in completely empty space, electric or magnetic field lines may exist. They just can't start or stop. They can't be created or destroyed, basically. And by the way, the magnetic version of this, it's the same thing. You can't have a magnetic field line that starts or stops, but we already knew that because that's due to the fact that there are no magnetic monopoles. So, and magnetic field lines in general are continuous. They don't begin or end in general in the universe. But so that leaves us with the two other equations here, and these deal with how those continuous fields behave. And it turns out that the electric field, you can create an electric field by varying some magnetic field in the vicinity. And same thing, if you vary some electric field, that will create a new magnetic field around it. And the weird property here is that it's not like if you apply an electric field upwards, a magnetic field develops upward too. The weird thing is that they're always going to be at right angles to one another. So if you have an electric field on the left-hand side of this, we're taking the curl of this. We're taking a cross product specifically. And any vectors within the cross product will always be completely at right angles to the answer for the cross product, for the result of it. So if the electric field points anywhere in the xy plane, the magnetic field must be at right angles to that. And that will always be true. So any change in magnetic field will actually produce a new, any change in the magnetic field will produce a new electric field at right angles to that magnetic field. And the same thing down here. When the electric field changes, if it increases or decreases, that causes a new magnetic field, but at a right angle to the electric field. And we'll see why, visually, why this is kind of cool, because you have electric fields going this way, magnetic fields going that way. When they change, all of a sudden we create new fields from those original ones. Again, this may not make sense much sense right now, but it will once you go through this this program here. So what we want to do now is find an electric field, ideally like some formula or a function for the electric field, and a similar one for the magnetic field, that when we plug them in, the left-hand sides of these equations will match the right-hand sides of these equations. Same thing right there. They also need to have the property that the curl, or that the divergence of them must be 0 too, but that's a whole nother ballgame. So the trouble with this is, in order to figure out what E fields would work, we need to know what the B field already is. And in order to know how the B fields would work, we need to know what the E field already is. So it's this circular reasoning that you can't get somewhere without knowing the other to begin with. So there's a name for this. This is called a first order coupled differential equation. So it's a differential equation. It uses differential operators, the del operator or ddt. It's a first order differential equation because where there's only one derivative at any given time. We don't see any second derivatives of space or second derivatives of time. But the important thing is that it's a coupled first order partial differential equation. It's a mouthful. It's a coupled equation. The E fields are tangled together with the B fields in the equations. They come together, and you can't separate the E fields and the B fields because you see both of those in the same equation. So what we want to do is decouple these equations. so that there's a single equation for B and a completely separate equation for E. So that would be a decoupled set of equations, and those are in general much simpler to solve. So here's how we're going to do this. We're going to take the fourth equation. And by the way, it could work equally well. You could start with the third and go through the similar steps. If you play at home, I don't know, treat yourself to a brownie if you do that correctly or something. So let's start with the fourth equation here. Let's take the curl of B, and that's equaling the changing electric field at right angles to it. But what we're going to do is we're going to take the curl of both sides of this equation. So it's going to look like this, the curl of the left side and the curl of the right side. And this looks ultra messy and confusing. But you guys have all had some quiz class. The left side you should immediately be able to see is there's a vector identity. So the curl of something is just equal to this thing minus that thing. And the nice thing here is that we see there's a gradient of a divergence, but there's the divergence of the magnetic field we know is 0. There are no magnetic monopoles. So this term completely cancels out, and we're left with the second term only. Now if we look at the right-hand side of this as well, in this case here, all we have to do is change the order of the differential operators. If you take the spatial derivative of the time derivative, that's exactly the same as taking the time derivative of the space derivative. So you guys know this in d dx dt is equal to d dt dx, something like that. So anyway, I'm just exchanging the order of the derivatives. I'm pulling the curl into this time derivative here. And now we see that there's a curl of E, and by the third Maxwell's law, we can just replace that with dB dt. And we still have the mu naught epsilon out there. And then we see there's a time derivative of a time derivative. That's exactly what we know as the second derivative, so simplifying it a little bit here. So what we've just succeeded here. Now if we combine this, the original fourth Maxwell's equation now becomes, we replace the left and the right-hand sides with what we just got. Now we have a second derivative in space of B is related to a second derivative of time, also of B. It's a decoupled second order equation now. Second order because there are second order derivatives now, and it's decoupled because we don't need to know what E is to solve for B, and vice versa. And that in general is much easier to solve. But so the question now becomes, what functions, what formulas could we plug in for B and somehow have the left-hand side equal to the right-hand side? So before we do that, let's go through what the left-hand side here means. You've probably seen this, the del square. This is just the Laplacian operator. It's the second derivative in x of the x component of b. So dx squared bx in the I hat. And the same thing, it's the second derivative with respect to y of by in the y direction. So the important point is this is a vector. It has I hat, j hat, and k hat, and it's also a second order derivative of x and then of y and then of z. Now the right-hand side, it has to be a vector if the left-hand side is a vector. But the right-hand side, if we take the second derivative in time of b, that's just going to be second derivative in time of bx in the I hat, second derivative in time of by in the j hat, and same thing here. Something on my porch just fell over. So the point is, though, the left and the right-hand side now have three separate terms: the x component term, the y component term, and the z component term. Same thing, x and a y and a z over here. And if the left-hand side equals the right-hand side, there's no possible way the x component over here could affect the y or the z. There's no possible way the y component on the left can have any influence on what's going on in the x or the z over there, and so on. So this actually turns out to be three completely separate equations. One equation that relates the I hat components on both sides. One equation that relates the j hat, and one that relates the k hat to each other. So it looks like this here. These three equations. So not only have we eliminated b from the picture, but now we've broken it up, and we have three separate equations. We have a single equation for only the x component of only the magnetic field, and a whole separate equation for the y component of only the magnetic field. So we're going to go through and we're actually going to make some trial solutions. We're going to try out a couple functions, see how they would work, see if they would solve this equation specifically just for the x component. Now, understand that we can do the exact same thing for the y component. We can do the exact same thing for the z because they're the exact same equation. But we'll just focus on the x component of b. So, first of all, if we look at any of these guys, it looks like the second derivative of a generic function f is proportional to the second derivative in space of that same function, where I'm just kind of generically writing alpha as any constant. So in this case here, we're going to propose a possibility. What if the second derivative in time of that function f was actually just proportional to that same function itself? For example, you can probably think of a couple functions that would work like this. One would be e to the x, or e to the kx. If you take the second derivative of e to the kx, you're going to get out k squared times e to the x. So pause that right now if you don't know how to get that. But if you take the second derivative of e to the x, the result is proportional to the original function itself multiplied by a constant, in this case k squared. Can you think of any other functions that behave like that? Probably the most obvious one and the most useful is the cosine function, or the sine function, exactly the same. When you take the second derivative of this, you're going to get negative sine and then negative cosine. So the second time derivative is directly proportional to the function itself, and the constant is just -1. So let's proceed here a little bit. Let's let that function not just be cosine, but let's let it have an amplitude, and we'll also let it have some other frequency, the omega here being the angular frequency. Now, when we actually solve these, we're going to turn it into the normal, the standard frequency, or the linear frequency in waves per second, not in radians per second. But we'll just do omega for now because it's one less letter than 2 pi kt. So anyway, we take the second derivative of this with respect to time. We get out negative omega squared times that original function. So make sure you understand that. So this has the property that we're looking for. The second derivative of the function is proportional to the function itself. So in this case here, we have the second derivative in space being equal to the second derivative in time. If the x component, or if the x derivative of that function is proportional to that function itself. And separately, if the time derivative, the second time derivative of that function, is also independently proportional to bx. In other words, if this function, when you plug in this, either the spatial or the time derivative, gives you back that same function multiplied by maybe 2 different constants, then we're good, because they'll both be proportional to each other. So you probably should go back and replay like the last 20 seconds, because that's actually an important idea. And that's what we're going to go on here. So if we want to check this here, we've already seen that the second time derivative of f gives us back our function, but the problem is there's no spatial dependence whatsoever. So that just gives us 0. So we're going to need to account for the fact that we also need to have an x in this. And how can we do that? So what we're going to do here is we're going to propose what we call an ansatz. That's A-N-S-A-T-Z, I think. Now, I first heard this word in my freshman year of my differential equations class. My professor had a very thick Romanian accent, and it's a weird word in the first place. And when you have someone with a thick accent try to pronounce it, it's completely indecipherable. But the word is actually pronounced ansatz. And what that means, it's a trial solution. It's an example solution. We'll just kind of go with a general idea, and we'll roll with it and see if it works. So this ansatz here is going to be, what if our function that had both x's and t's was actually 2 separate functions, one that only depends on x, multiplying one that only depends on t. If that's true, the product rule will act in our favor here. And so that's what I mean here. If the second derivative of x is proportional to x, or f, second derivative of g is proportional to g, then watch what happens. Second spatial derivative here, when you plug in the expression for b, g of t is essentially a constant when we differentiate with respect to x. So g of t falls out. Now we use the fact that the second derivative of f is just proportional to the function itself. So there's going to be some proportionality constant here to make that equation completely true, but I don't care. But the point is, we've just shown that this thing here that we get out, the proportionality function, is exactly the same as what we started from. And it works for the time direction as well, too. We take the second time derivative, when we break it down into the two separable functions, f of x is like a constant because it has no time dependence, so we can pull that out. And then now, again, this will be proportional to g itself. So both of those functions, sorry, both the derivatives will actually be proportional to one another because they're proportional each to b sub x. Again, this is another one that you may want to watch 2 or 3 times to fully see what's going on, but the importance is the second derivative matches the original function times a constant. Yeah, that. So let's actually get a little more specific now. Let's take a cosine as the basis for these functions. We've already seen that works. And for the x side, we're going to look at the amplitude times cosine of 2 pi kx. For the time, it's going to be times 2 pi f, or the argument is 2 pi ft. Now, you're probably familiar, you've seen this, just the standard frequency, just in waves per second, or hertz is another way to measure that, H-E-R-T-Z. So it's a little different than the angular frequency. There's the 2 pi there, but it's just how quickly the waves, how many waves per second we get. The other one here, the k, this is probably the first time you've seen this. This is what we call the wave number. What's happening? This is what we call the wave number. And this measures not the number of waves per second, but the number of waves per meter. So you can think of the wave number as really kind of like the spatial frequency. This is the time frequency, how many per time. This is the spatial frequency, how many per length, how many per meter. And just as an example, you can read this diagram thingy that I threw in there. But that's what a wave number is. It's the 2 pi kx. So when we look at this here, if we take the second derivative of f with respect to x, second derivative of g with respect to t, this is all basic calculus, and you can see that what we get out is for the x component of this, we got minus 2 pi k squared times our original function, or minus 2 pi f squared times our original function for time. So that brings us to, what if our magnetic field was expressed as a combination of these two functions that we just found their second derivative, modified by just a single amplitude here? And by the way, that would provide the proper units for b as well. So if this was our actual solution, provided by our ansatz, the separable functions, then let's look what would happen. Here's the second derivative with respect to x. We just get out our 2 pi k squared. The second derivative with respect to time comes only from looking at the g function right there. So when we put this all together here, the way to check whether we did this, here's our original function. Here are the derivatives. Now we need to plug these into our Maxwell's equation. We need to see whether the left-hand side here will actually match the right-hand side for the exact function we've just created. And at this point here, this is fairly straightforward. We're just going to throw that in here on the left side. We'll substitute this whole thing over there. And this is the equation we need to satisfy. If the left-hand side matches the right-hand side, we're good. So let's do some cancellation. Negatives, blah, 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 2 pi's. So we end up having something that looks like this. K over f squared times our function may or may not equal mu naught epsilon naught, also times our function. Now, we have a bx there and a bx there. You can replace that with our entire function, and we'll see that those will both cancel. So ultimately, the question we need to ask is, does our ratio of k over f match the actual numbers of mu naught epsilon naught and the units? Or more specifically, when we construct our function, as long as we very meticulously take k and f to have this property here, if the ratio of k over f that we create has the same magnitude and the same units of this right there, those are the exact functions that will solve Maxwell's equations. So the criterion for this function that we created being a solution of Maxwell's laws is whether this equation is true for the given k and f. And so I'm actually, when we talk in the next page here, I've flipped the order. I've just taken the inverse. You'll see why here, hopefully in a second. But so this is what we're going to work with here. So first of all, let's look at the units just of this ratio F over K. F is waves per second, the frequency. K is waves per meter, the wave number. Now, if we take the ratio, pause this for a second, do this for yourself, you'll find out that the ratio here is actually meters per second. Turns out this F over K from our criterion for solving Maxwell's equations, the F over K actually just represents a velocity. And specifically, if we fine-tune our F's and our K's so that the actual velocity matches whatever that is, the square root of 1 over mu naught epsilon naught, if this actually is true for the function we're talking about, then we have just solved Maxwell's equations. So again, this has to be some sort of a velocity, and if it's equal to that, we're good. So at this point here, I'm going to encourage you to pause the video and to actually numerically and looking at the units solve this here. So make sure the units check out to be a velocity. Also numerically find your answer for this, 1 over those fundamental constants, mu naught epsilon naught. So I'll pause for a second. I'm going to drink some wine. No. So anyway, those of you who paused and you got the answer, you should be thoroughly astounded. Those of you who actually don't want to do the work and just want me to do it for you, prepare to be astounded. This is actually pretty crazy here. So let's look at this. We're going to plug in values, and these are what we've been preaching all semester. The units are correct here. There's a couple other ways to list the units, but I think these are the most convenient for our purpose. So if you didn't actually work through this previously, do this now. What you're going to find, here's the numeric answer, here are the units. The last step here, this equals the square root of this thing. What we get is this equals the speed of light. This is not a coincidence. This actually is the speed of light. And so let's go back to what that means. We've said that if our ratio of F over K equals V, in other words, if the velocity of this magnetic field that we've created has a property that it equals 1 over mu naught epsilon naught, if the velocity of this magnetic field equals that, then we're good. And turns out the velocity that it has to equal is the speed of light. This is what this means. The only solutions to Maxwell's equations have the property that they propagate at the speed of light. And specifically, these solutions are combinations of electric fields and magnetic fields at right angles to one another. Those electric fields and magnetic fields carry with them energy at the speed of light. And that's exactly what light is. Light is the propagation of energy stored by the electric and the magnetic fields that solve Maxwell's equations. In other words, they have this exact velocity. So if you're curious about this stuff, it's more than a coincidence, obviously, that this works out, but it's just kind of, you would never really predict this, and nor did Maxwell until he actually went through and solved his equations and found that the answer that he was looking for was exactly the speed of light, and he actually had just created light. And that's historically why it's so important. It was almost stumbled upon by accident, that he didn't know that he was actually solving the equations that govern how light behaved, but that's in fact what this is. So those of you who are interested in this, there's a little more to it, and as you know now, we understand, we found out in the early 1900s that light actually travels as packets of waves bundled together. We call them wave packets, or yeah, whatever. But those wave packets are photons. Those photons they behave like particles, but they also have these wave-like properties. And this is the basis of quantum mechanics. How can something be a wave, but also be a single particle like a billiard ball or something? It doesn't seem to make sense. And those of you who are interested in this, this is exactly what we cover in modern physics, which I will be teaching next spring, spring of 2017. So those of you guys who are still around want to have fun with this for a whole semester. So the whole point here, we have just found a single solution to Maxwell's equations. Now, a couple caveats, a couple things to point out. We only were looking at the x direction. We only solved it for b. We didn't then go back and actually figure out, well, if b looks like this, what does e have to look like? That's exactly what you're going to do on your worksheet. So, but you're going to use a lot of the same techniques we used here. Also, I want to note that there is more than one possible solution to this. So the one that I've used here, I think as you go through that worksheet, you're going to see how it's not actually doing much for us. That there's better solutions, and you're going to explore exactly one of those to see how that works. And then, just as a preview, what you're going to find. when you actually go and work back from B to get E and so on, you're going to find that you have two mutually orthogonal or mutually perpendicular fields. The electric field points in the x direction, the magnetic field pointing in the y. They're going to change. They're going to get bigger. They're going to get smaller. And they're going to propagate in the z direction here. This is exactly what the solutions of Maxwell's equations do imply. And just to show you a quick video on this, not that, this one here. This is what it would actually look like. The electric field's in the blue, the magnetic field's labeled oddly as H. Don't worry about why that is. But this is what they will look like over time as they travel. This is how light carries its energy. It carries it as waves that move together. But if you look at how they behave at a single point, think of this as like the receptor on your eye, we see the electric field is constantly varying, positive to negative to positive to negative. The magnetic field is constantly oscillating, left, right, left, right. And it's this mutual oscillation of these fields that allows them to propagate forward. If one changes, the other changes. So I don't want to give too much away here, but it's pretty cool to see how light actually works. So anyway, I hope this did make sense. And again, please go through your Maxwell's equations packet now because I think it actually go pretty smoothly. So cool.